All right, so today's topic deals with shifting equilibrium, sometimes called Le Chatelier's principle. Okay, so once we understood that reactions were reversible and that they can reach, instead of an endpoint, they're actually reaching a dynamic equilibrium, it was our job to figure out how to drive that equilibrium in the direction we wanted it to go. So Le Chatelier's principle states that basically, if you have a system that's in equilibrium, you can shift that system. You can change the equilibrium as a result of various stresses by changing things like concentration, changing things like temperature and pressure. Okay, so when an equilibrium is stressed, the system will adjust to minimize the effects of the stress and establish a new equilibrium where the proportions of reactants and products will be the same, but the amounts of reactants and products will be different. So why does this happen? Well, the system wants to be at equilibrium. So if you stress it, if you change that equilibrium, then it's going to shift to get back to that equilibrium. So what does that mean in the context of stresses? So here's a little device you can use to just help you memorize Le Chatelier's principle. So if you increase a factor, whether it's concentration, temperature, or pressure, the shift will be away from the increase. So if you increase something, then it shifts away from that increase. And if you decrease something, then the shift is toward that decrease. Okay, so if you're visual, here's a system in equilibrium. We can use a teeter-totter to illustrate balance or equilibrium. Okay, so if you increase a factor, then the teeter-totter is going to tip in that direction of increase. So what's going to have to happen? Well, it's going to have to shift away from that increase. Okay, so that it will reestablish the balance. The amounts will be different, but the proportion will be the same. Okay, so if you increase a factor, then the shift is away from the increase, whether it's a reactant or a product, or whether it's temperature or whether it's pressure. Okay, and then decreasing a factor, and the shift is towards the decrease. So let's look at each of these in terms of how they specifically play out. So with concentration, what is the effect of an increase or decrease in reactants or products? So if we look at the decomposition of carbonic acid, so this happens every time you open a pop, a soda pop, CO2 is produced, so you end up with carbonation, carbonated water, CO2, and water. So what happens if you increase the CO2? Well, that's how they make carbonation. They take water and they bubble CO2 into it. So you end up with carbonic acid. If you remove CO2, like when you open a pop bottle, the CO2 is allowed to leave, so you end up with the production of more CO2. The shift is in this direction. Okay. What about temperature? Well, it's helpful to think of heat as a reactant or a product. So it basically a thermochemical equation. If you see where heat is as a reactant or product, then the following will hold sway. By increasing the temperature, it causes the equilibrium to shift away from where heat is in the equation. Okay, so if we increase the temperature, heat's on this side, so increasing this factor shifts it away from the increase. Okay, so first of all, think, is this reaction and or exothermic? Well, heat is a product, heat is being given off, so it's exothermic. So for exothermic reactions, if you want to maximize an exothermic reaction, you can't heat it up more, you have to cool it down. So if we add heat, the shift is toward the reactants, so the reaction will be less efficient. So we have to remove heat. We have to cool the system down in order to keep the system going in this direction, we want to shift it to the right. What about this? Is this endo or exo? Well, heat is a reactant, so it's endothermic. So how do we maximize product? Well, it takes heat. This reaction absorbs heat. So if we add heat, it will shift towards the product. So to maximize product, we want to add heat for endothermic reactions. If we remove heat, then the shift is towards the reactants. Now, what about pressure? First of all, pressure only affects gaseous systems or systems that have at least one gas as part of their reactants or products. So, and it only affects gaseous systems that have an unequal number of moles of reactants or products. So the first thing you have to do if you're dealing with pressure is look at how many moles of gas are on each side of the equation. If there's no gases, then pressure has no effect. If there's only gas on one side of the equation, then you need to take that into account. If there are gases on both sides, then you need to count moles of gases and see which has the most moles. Okay, so an increase in pressure shifts away from where the most moles of gaseous components. So you count the coefficients of gaseous products or reactants only. And then a decrease in pressure shifts towards the most moles of gaseous components. Okay, so here we have a very important chemical reaction, okay, the production of ammonia. Okay, and if we look at the number of gases, there's 1 plus 3 is 4 moles of gases of reactants, and 2 moles of gases of gaseous products. So if we increase the pressure shifts away from the most moles. There's the most moles of gases on this side, so it would shift away from that. It's going to affect this side more. So increase, and you shift away from the increase. Okay. Whereas a decrease in pressure shifts towards where the most moles are. So a decrease in pressure shifts back towards the reactants. Okay. So how can you increase the pressure on a gaseous system? Well, one way is to have it in a sealed container and then be able to affect the volume. So if you decrease the volume, what's going to happen to the pressure? You increase the pressure. Okay. So if we think about what are all the things, if we put heat in this equation now, what are all the things we can do to shift the equilibrium towards a product? In other words, we want to maximize the production of ammonia. Well, the first thing we can do is maximize the amount of reactants. If we increase the reactants, it will shift towards the products. Second thing we can do is, as the product is being produced, we can remove it. We can decrease the amount of product. And if we decrease the product side, then the shift is toward the decrease. Also, since heat is produced, if we remove the heat, in other words, if we cool the system, we have a cooling system in this reaction, it will also maximize products. And then the last thing we can do is alter the pressure. We want to keep it at a high pressure, since pressure will drive it towards the products. Okay. And this is just a diagram showing the different things they do in the production of ammonia. It's called the Haber process. Okay, so here we have a reversible reaction, just a generic reversible reaction. 2 moles of A react with 3 moles of B. It requires heat, so it's endothermic, and it produces 3 moles of C and 2 moles of D. And then here are the equilibrium concentrations, and we'll talk about what those mean in the next discussion. So we're going to have a stress, and I want you to predict what the shift will be. Okay, and we'll talk about the answers at the end. So if we increase the concentration of B, what direction will the shift occur? What about lowering the temperature? What effect will lowering the temperature have on this equilibrium? What about decreasing C? What direction will the shift be if we decrease C? What about increasing pressure? And what about decreasing the volume of the container? Okay, so increasing the concentration of B. When you increase something, the shift is away from the increase, so it shifts towards the products. Lowering the temperature, it takes heat, so if we lower the heat, then the shift is towards the reactants. Decrease C, if we decrease the products, decrease the factor, the shift is toward the, so the shift would be towards the products. And then increase the pressure, there's two moles of gas on this side and none on this side. So if we increase the pressure, the shift would be towards the reactants. And decreasing the volume, if we decrease the volume, it increases pressure, and increasing the pressure, we all have already decided, shifts it towards the reactants.